I wasn't able to get it to work perfect, right? Gave me a, so I had to go redo them.
Oh man.
Yeah.
All right.
Turns
So
out like 4 of these.
I'm gonna get started. I got good news and bad news for you guys. The bad news is we have new homework assignment. The good news is I'm gonna talk about it. So sort of, bad news, good.
Pros and cons.
Some people look at it as both bad news, but that's a choice. All right, so I will start with the homework assignment because I like to do this, do things this particular way to motivate people to take notes and pay attention in class because now they can try to relate what I'm going to talk about with something that they have to do as homework assignment. This is way too loud. So I'm going to put it on and then I'll adjust the volume. There we go. All right. Let's see, is that working? Is that working? I think that's about, is that good? A little more?
The bottom of the mic fell off.
Oh, that's the wind screen. Which means I have to turn it off first before I put it on. Just the wind screen. It doesn't really matter when I put it here because I'm not blowing any air on it. But the next instructor may put it somewhere else. I cannot imagine how where else they can put this where the windscreen is actually needed. Probably don't want to know either. All right. All right, so this is your new homework assignment right here. The other ones, they're all grayed out because, I'm not going to give you guys, those particular ones. So let's go ahead and click on this one. It's called CNF assignment. One person asked me and said, but we haven't really talked about CNF yet. What am I going to do with this homework assignment? Well, that's exactly what I'm going to talk about today. Okay, so we'll talk about conjunctive normal form. That's what CNF stands for. So we'll talk about that. All right. So the homework assignment is about this expression, but just to make it not so dry, I'm going to assign meanings to each variable. CISP is a boring class is P. Okay, so variable P is representing the statement of CISP 440 is a boring class. Now, once again, this is not an assertion that CISP 440 is actually a boring class. It is simply a statement that can be true or false. Is that okay? And then the other three are basically the same nature. TAC is teaching CISP 440. Once again, it's not an assertion. It is simply a statement, a condition that can be true or false. A gamer is taking CISP 440. Same thing, it's a condition, can be true or false. And someone sleeps in CISP 440. Oh, 400. Okay, I got the wrong class here. Got to fix it. Because otherwise, whoever is teaching 400 may not like uh-oh.
It's Fox. I wouldn't worry about it.
Is he still teaching 400? I thought somebody else is.
You use that word teaching liberally, right?
Sorry?
Whoa.
I thought somebody else is teaching 400 this semester, but I
We're
couldn't.
recording,
Well, I am on recording. Jokes and jokes.
I'm gonna link him.
Haha, jokes. Okay, so somebody sleeps in CISP 440. Okay, I can pick on myself. All right, so each one of these, okay, P, Q, R, S, they are all variables. Okay, and because they are all variables, we can make a well-formed formula out of these variables and the connectives that we can usually find in logic. So in this case, we have Q or R, okay, in one expression. Together, they imply P, okay? This is one part of the conjunction. The other part of the conjunction, or another part of the conjunction, is P implies S, and then the last portion is just S itself. So when you read it as English, okay, it basically means TAC is teaching CISP 440, or a gamer is taking CISP 440, implies P, cisp440 is a boring class. The second one in the conjunction is basically saying P implies S, which is cisp440 is a boring class, implies someone is going to sleep in the class. And the last one is all by itself, which is somebody sleeps in cisp440. Okay, so once again, this is an expression using those variables. This entire expression itself can be true, can be false. I am not asking you to prove anything. That's for the next homework assignment for next week. Okay, this one is just asking you to transform this particular well-formed formula into a CNF well-formed formula, which is going to be the centerpiece of today's lecture. Okay? So the transformation is going to be something that we'll talk about today. I will leave this page up because I think there will be people asking me questions once we get to the material. When you do this homework assignment, you have to show all your steps and quote the rule or the law that you use in each step, because I want to know exactly how did you get from one step to the next. All right, so are there any questions about the assignment itself? I understand CNF, I have not talked about CNF yet, so that's what we'll talk about next. But other than that, are there any questions about the homework assignment? Yes?
When you say local law rule, that's all the axioms we have, not just axioms?
Not the axioms. There are specific rules that you use to convert something into a CNF. So we'll talk about those rules. But that's a good question. I'll explain to you what you need to quote and what you do not need to quote. Right? So I'm going to leave this one up. And the note that talks about what you need to know to get this homework done is in normal forms. Okay, so we'll go ahead and take a look at that one. So we might go back and forth between these two tabs, the first one being the homework assignment, and the second one being the discussion of what is a normal form. A normal form is basically a WFF, a well-formed formula, that conforms to a certain format with restrictions where certain operators can only be used at a certain place. If you are taking CISP 310 this semester, you already know one of the normal forms, okay? Because in that class we use a DNF, or the disjunctive normal form. In this class we're using the conjunctive normal form, which is kind of the opposite or the dual part of what a DNF looks like. So we'll talk about what is a CNF here. If you want to look at it in a very brief way and describe it in one single sentence, a conjunctive normal form is a well-formed formula that is a conjunction of disjunctions, and the disjunctions consist of at least one variable, consists of only variables and negated variables. Okay, there are several ways to look at this. One way to look at this is from the gate perspective. So if you look at it from the gate perspective, you have a big AND gate that is the last stage. And then in the earlier stages, each one is a disjunction. So that's one way to look at it. So for those of you who know what a gate is, this is how you look at it. And then the output of all the OR gates feed into the AND gate. And then with each individual one, you can have negation or not. And then these all come from variables. So these three may come from one single variable, and then these two may come from another variable. This one can go to this one, can also go to this one from another variable, and so on. This is from the perspective of gates. If you don't have any exposure to logic gates, that's okay. We can still look at this from the perspective of variables and expressions. So the other way to look at this is at the lowest level, okay, you basically have variables. In the homework assignment, we only have 4 variables. We have P, Q, R, S as variables. A variable by itself, like P, is already in conjunctive normal form. So this is okay by itself. If you have a conjunction of this with something else, that's okay too. Because in this case, P is in conjunctive normal form, Q is in conjunctive normal form. So when you have a conjunction of these two, it is still in conjunctive normal form. So when does it not become conjunctive normal form? This is not in conjunctive normal form because the OR or the disjunction has to be performed after the conjunction. The disjunction, the OR, is performed after the conjunction. So if you draw a picture of this expression, the disjunction is the last thing that you do. What you supply to the disjunction on one side is R, on the other side is the result of the conjunction. And the conjunction in this case involves P and Q. So that is not in conjunctive normal form.
Okay, so the last order, the last, like the overarching operator has to be the conjunction.
Correct. So when you look at an expression in a structured way, I want the conjunction to be all the way up here, whereas below we can have any number of disjunction. Okay? Yep.
So changing the parentheses would not change the order. So if Q and R were in parentheses, would that change the order or not?
Which you would change.
In this case, because of the use of the parentheses, you have to perform the conjunction first.
Okay. But if it was the other way around, we do
If it is on the other side, yes, then it would be a conjunctive normal form. So you're correct. Let me just write it out too. So the alternative, or the other way to arrange the parentheses, but that actually changes the meaning of the expression. So those two expressions are not the same, but we're just talking about, okay, what if you have the parentheses around Q or R? Okay. That is in conjunctive normal form because you have to perform the disjunction first, and then you perform a conjunction as the last operation. Okay. Very good. Good. Negation can be applied, but negation can only apply to individual variables. You cannot have a negation applied to a disjunction. You cannot have a negation applied to a conjunction. Is that okay? Yep.
So if you do have it applied to it,
You have to transform it. Yeah, you have to use one of the three mechanisms to make it into a conjunctive normal form. So the theorem is any expression, any logical expression can be transformed into conjunctive normal form. So it's just a matter of how you get about doing it. Yeah, go ahead.
Can the CNF have conjunctions in it as long as the disjunctions?
No. So the conjunction, there can only be kind of like one gigantic conjunction at the end. This can have any number of components. But each component of the conjunction has to be a disjunction. There are a few exceptions, okay? A variable by itself does not fit into this particular structure, but it is still considered as a conjunctive normal form. Because you can force it into a conjunctive normal form if you want to, because you can always say this is P or false, right? And then the whole thing and truth. That turns it into conjunctive normal form, but without changing the actual meaning. So we don't do tricks like that. Okay? We just basically say a variable by itself is already in conjunctive normal form. P and Q, P or Q, is also in conjunctive normal form already if this is the entire expression. Okay? Because if I want to turn this into a conjunctive normal form, I can just put parentheses around this and then say and 1. Okay? That doesn't change the meaning, it just forces the structure of performing a disjunction first and then do a conjunction later. But it's just extra work, so we just say that, okay, we'll just say that this is already in conjunctive normal form. Is that okay? If you have negation of P, that's in CNF also. Okay, so a negation can be applied, but only to individual variables. In the second one, if you have not P, the whole thing, or not Q, the whole thing, that's also in CNF. Okay, because not P by itself is just one component, and then not Q by itself is just one component. Is that okay? Are there any questions about what constitutes a conjunctive normal form? Yep.
Is P and Q in CNF?
Yes. Okay, so to make that conclusion, what you say is if phi is in CNF already, is in CNF, and psi is in CNF. If these two components are in CNF already, then phi and psi is also a CNF. Yep.
When determining if it's CNF or not, should we usually draw those trees to help us determine if it's conjunctive or disjunctive at all?
That will help. Because in general, they will have this particular structure. It's just that when we're dealing with these simple cases, that they do not actually fall into that general structure.
I didn't know the process of gates, so the linked trees kind of are mildly confusing. Can we go into what that tree actually means? Because the top part is the conjunction itself, and it branches off into disjunctions.
Well, okay, let's consider normal arithmetics. Okay, so this, let's not use PQRS because that will just add to confusion. So let's say I plus j, the whole thing times k. Okay. Oh, change it to k. So in this case, I rewrite this expression with the multiplication on top because it's the last operation.
Okay.
So that would have k on one side, and then on the other side would be the sum of I and j.
Oh, I see.
And that's basically what I'm using here to represent the structure of a CNF.
I see.
Yep.
I have a quick question about how we submit the homework. Does it have to be a text file or can it be a scanned picture, like if you work it on a paper?
I would rather not look at a scanned picture because of various styles of penmanship. So you can use one of the standards for logic expressions. Okay, you can use the equation thing, which I think most people do not like to use. Okay, you can also use another notation. This I can actually just show you in a text editor because I think if you're thinking about typing it, this can be a time saver. So let's say the original expression is P. Okay, I'm just going to spell out the words. So we'll say P and not Q. Let's make it more complicated. So one side has or R. Okay, there we go. Okay. And if I want to emphasize the negation only applies to a variable, is that in CNF?
Yes.
Okay, it is. Yep, go ahead.
You meant it to be Q or P and not P?
Oh, Q. Yep. Here we go. All right. But it is still in CNF. Whether it's P, Q, R, or S, it is still a variable, and the negation of a variable is still the same. Okay, so I want to show you, the engineering notation because you're also in CISP 310. You can use the same notation in this class. So the P, you can basically use just a multiplication to indicate conjunction. So you can basically say, in this case, I cannot do an overbar, so I can use prime to indicate it's the negation of the thing before that. So Q prime is not Q, and then the plus can be used for disjunction. So you can write it as this if you want to. But you have to be careful because the prime applies to whatever is before the prime itself. So Q prime is the negation of Q. So it's not like the other negation symbol which goes before the variable.
You don't want us to use like exclamation mark? That would be
Exclamation point for the multiplication?
for negation.
For conjunction?
Negation.
For negation? You can do that too. So if you want, okay, let's just fix it and use the exclamation point. I think that's the easiest.
I like it much more.
Okay, that's fine. So that makes it a lot easier to write. Yep.
How could phi not be CNF?
Phi?
Yes, phi or phi.
This is
Yeah.
This is phi.
Yeah, how could one of them not be in CNF?
They can just not meet the requirement of a CNF. They just don't have this structure. I can give you a very simple non-CNF. That is not in CNF. Because the negation applies to an OR. That's it. I don't even need to know what's inside. I just know that the negation is applied to the result of a disjunction. Is that okay? It is still a well-formed formula. So we are not talking about the differentiation between what is a well-formed formula as opposed to what is not a well-formed formula. Because within well-formed formula, we have things that are considered CNF and things that are not CNF. Yep?
But isn't that the same as N1?
Isn't that the same as?
N1, like V1.
That is correct. Okay, fine. But in order for something to be a disjunctive normal form, it has to fit into this structure or this structure here. This one doesn't fit it because there's a knot. The knot is here in between the result of the OR and the input of the AND. And that's why it is not in CNF. Yep.
If you were to distribute the knot, would it then be in CNF?
Yes, but then you are applying the Morgan's law to transform it.
Okay, but I was just making sure.
Yeah. So we'll talk about how to transform it.
That's the homework assignment basically, right?
That is basically what your homework assignment is about, is to apply. There are 3 particular rules that are useful to turn anything into CNF. And we'll talk about that in today's class. Are there any questions about this? No questions. Yes, go ahead.
The not E or not F, that not CNF.
Which one?
The one on, yes, that one.
That one is a CNF because not P is a CNF. No, I take it back. Each component of the OR can be either a variable or the negation of a variable. P is a variable. The negation of a variable is okay to be inside the disjunction. Q is a variable. The negation of Q is also a component that can be inside the disjunction. If you have a disjunction all by itself, it is still considered a CNF. Because you can just say the whole thing and 1, yeah, which doesn't do anything. Yep.
You're recording, right?
I sure hope so. Yeah.
Okay.
And the voice checked. Yep. So everything checks out. Yep.
Can you say?
Looking back at the diagram, where was the conjunction of disjunctions? Can you have a conjunction of a conjunction of
No.
disjunctions?
Nope. Nope. It must be like this. Yep. The only place you can have a negation is down here. Then you can have negations. Yep.
Can you repeat that rule one more time?
Which
for
one?
the bottom right there? That each component of the
Disjunction can be either a variable or the negation of a variable.
So that's not a well-formed formula then?
This one is well formed and also a CNF.
Okay, so a variable and or a WFF is okay?
Okay, so let me see if I can just kind of write it down on my notepad here. It is also discussed in the notes here, but we'll talk about this a little bit. Okay, so P is a CNF, right? Or is in CNF because not P is in CNF. Okay, P or Q is in CNF. Not P or Q is in CNF. Because if you just have a variable or the negation of a variable and you only have those components inside the disjunction, that disjunction is still a CNF. Okay. And then the rest is recursive because the rest basically says, if phi is in CNF and psi is in CNF, then phi or phi and, okay, it's hard to Okay, I'll just spell out N here. Psi is also in CNF. You can make the string of conjunctions longer and longer and longer, but each component of the conjunction has to be a disjunction, and then on top of that, each disjunction can only involve either variables or negations of variables. That's basically the rule. Yep.
For the line above that sentence, did you mean to say not P plus not Q?
No, that's not P plus just Q by itself.
Okay.
So the negation only applies to whatever is right after that. So without parentheses, it only applies to P in this case. So basically, this is the same thing as not P all by itself. Any other questions about what is CNF? What is conjunctive normal form? Yep.
What do you mean variable? Because my confusion right now is between P and psi, where P,
Okay.
for instance, is a variable in unit.
Okay, remember the alpha set?
Yeah.
Okay, the alpha set has three types of symbols. It has symbols representing constants. So the constants, the constants can only get their meanings from iota. And nothing else, can define the meaning of the constants. The second type of symbols are the variables. And the variables can assume either, well, in this case, because it's Boolean, it can assume either constants. But sometimes it's unknown. Okay. And then we have the Greek letters. Remember, we have psi, phi, and rho. Those represent well-formed formulae in general. They're basically a placeholder to represent any well-formed formula. So that's why in this case, when I refer to something that is a well-formed formula, I use the Greek symbols. I use phi and psi in this case. Is that okay? Yep, go ahead.
So if we had phi is the P and Q or R, right? The one right above it.
Yeah.
And psi is the one over on the right with the
This one?
not P, yeah.
Yeah.
I mean, whatever. And then, so if you say phi and psi, there's two conjunctions nested in there, and that's okay?
No,
There's
no.
the conjunction in phi, and then the conjunction of phi and psi?
Yeah, because when you combine this one with this one, right? Then it becomes P and, okay, and then the second disjunction term is Q or R, and the third one is not P or not Q. So you still fit it into this category because you just have, I think, two ORs. One does not have an OR, but it is by itself a CNF. And then because you have a conjunction of all of these CNFs, the result is still a CNF. Yep.
So when we don't have parentheses, we just go left to right as normal.
If we don't have parentheses, then we
In
go.
parentheses, we just go from left to right. Like if we had a series of conjunctions and disjunctions of variables, we would just go from left to right.
I'm not quite sure what you're asking.
Like
When you're reading it, sorry?
If there was no parentheses,
Uh-huh.
what's the order you would go in?
P and Q and R, like in one line without parentheses.
Then it is,
Left to right.
okay, the ands are, conjunction and disjunction, they're both commutative, so you can exchange the order in any way you want. If you're talking about P and Q or R, that is not good because, in this case, the general rule is it is implied that conjunction has a higher priority. But in your homework assignment, I want it to be explicit, so you just use parentheses to indicate the order of application. Yep.
And, okay, so if we weren't to use parentheses, if we used like P or Q and R, that would be the CDF form.
Okay, so if without the parentheses, like this one,
No, if we use, because the way I see it is if you don't use parentheses and you have a conjunction on the left-hand side, then that's bad if you're doing the conjunction too early. But if you have it on the right-hand side, then it's okay.
okay. Because
I would still rather you to use parentheses to clearly indicate how you group your operations. Yep.
Is that because it's not considered a raw form formula when it's not when you're not using the parentheses?
When you're not using parentheses, then I can only you are implying the order of operation, and I don't want anything to be implied. So I would much rather you guys to use parentheses to clearly indicate how you group the operations.
Oh, so it's just for visibility.
Right.
Okay.
Yep.
I'm not sure if I'm making this up, but so go back to Nathan's question. So like that form that you have in the green parentheses, that can exist inside of that tree that we have. Like
You can take out the parentheses.
Well, I'm not concerned about the parentheses. I'm concerned about the conjunction that's inside of it, because I'm under the pretense that we can only have one of those operators inside
Correct.
the entire structure.
But the conjunction, okay, when you have something like this, and then you have an and, not P or not Q, something like that,
Yeah.
okay? The disjunctions, they're all operating at the same level. So that means when you have something like this, you can take out this parentheses without actually changing the meaning of the operation. But when you write it out, when you combine those two, you still have to take out the parentheses to make it, turn it into this form.
But if we had a tree of that structure, one of those nodes would have a conjunction.
Correct. That would not be a CNF.
Okay. So
Yeah.
it wouldn't have. I thought you said.
That should not happen. So when you have something like this with a conjunction, and one component of the conjunction is like this.
Yeah.
So let's say we have A, B, and C in this case. Okay? This really is the same thing as a big, huge conjunction that has three components of A, B, C. So you just basically flatten it, the tree, to this like that. It's just like addition, right? If you don't look at these as conjunction, and instead they're addition or multiplication, it doesn't really matter how right, left associativity does not really matter. So you can flatten the whole thing and just say, okay, we have one combined conjunction or one combined addition to combine all of those operations.
I think it's like the binary nature of it. That seems like you have three operands to an operator that only takes two.
Correct. Normally they are binary operators, but when we have a whole series of binary operators of exactly the same kind, then we can collapse them into one single structure like that. Okay, there was another hand somewhere. Yep.
So as long as we're not forced to do conjunction before we can resolve all the disjunction, then that part of it is cleared up, right?
Okay, say that again.
If we're not forced to do conjunction before all of the disjunction can be cleared up, so it might
Correct.
be written in a way where you could do
Yes.
conjunction over here.
Yes, but you also cannot have a negation of a conjunction or the negation of a disjunction. Any other questions? Okay, let me see if any other people can explain this a little bit better, because the whole thing about conjunctive normal form is not my idea. I cannot take credit for that. And conjunctive normal form in Wikipedia, and it is explained as all conjunctions of literals and all disjunctions of literals are in CNF. Okay, we kind of explained that. As they can be seen as conjunctions of one literal clause and the conjunction of a single clause respectively. Examples and non-examples. Okay, let's go through some of these examples. Okay, this is in CNF. All of these are in CNF. Are there any questions about any one of these? Do they conflict with what I just said? Do they add to what I just said?
Just since we're up here, can we draw a tree for the second one?
The second one? Sure. Okay. All right, so to draw these trees, you start at the bottom level, okay? So at the bottom level, we have A, B, and they are connected by an OR. That's the first expression of the second example. Is that okay? And then the second expression has not B, C, D, and not D as individual components, and they're all connected to the same disjunction. The third one is D, not E, as individual components, and they're all connected to the same disjunction operation. The result of all these disjunctions are connected to one overall conjunction. So that meets the requirement that we were talking about earlier. Okay, so this is how you can look at it. Is you have 3 layers. The top layer has to be a conjunction. The conjunction can have any number of components, including 0. And then the second layer, they have to be disjunctions. And then the third layer can only be variables or the negation of a variable, of variables. So that's one way to look at it. Yep.
Sorry, can you repeat what did you say about the second level?
The second level?
Yeah.
The first level is conjunction.
Yes.
The second level can only be disjunctions.
Only be.
Yes. So the result of each disjunction of the second level will feed into the top level conjunction without any negation. Okay? You cannot have negation here. And then the third level are either variables or the negation of variables, and they can feed into the disjunctions. Yep.
Why is it so important to only negate the variables and not the?
Aha! That's a very good question, but I got a better one. I got a better one, and I'm kind of surprised that nobody asked the question. I'm pretty sure someone has the question and decided, well, maybe I should not be asking that particular question. And that question is, why do we care about CNF? After all, we remember what I said. Any well-formed formula can be re-expressed in CNF, right? So that means CNF is probably not any more expressive than what we already have. So what is the whole point? Okay? It is not a part of your homework assignment yet, but it will be. So I'm going to give you a fast forward to what we'll be doing probably next week, possibly Thursday. It has to do with resolution. Has nothing to do with New Year, but it's a mechanical process, okay? So we'll just take a look at one step of resolution, and you guys can tell me whether it makes sense or not, okay? So we have 2, okay, first of all, is this in CNF?
Yeah.
Okay. Assuming each one, phi, psi, they're all individual variables, okay, which I used the wrong symbol here, it should be just P, Q, R, S, and so on. But if that was the case, that's in CNF. Does the conclusion make any sense? Okay, let's take a look at the left-hand side first. So the left-hand side said right here, it says phi or psi, okay? We don't know whether psi is true or not, whether psi is true or not. We just know that these two can be combined or be connected using a disjunction. The other side says not psi or rho, okay? And once again, we don't know, individually whether they're true or not. But one thing we know for sure is psi and not psi cannot both be true at the same time. Okay, that makes sense because they're negations of each other. So the question is, using this on the left-hand side, is the inference making any sense? Can we infer that rho or phi is true?
Yeah.
Does that make sense? Can we make that conclusion? Okay. This can be done mechanically. You just sort out everything and you locate 2 terms out of a CNF. So look at these things here and you say, I want to find 2 of these things where one has the non-negative version of a variable, the other one has the negative version of the same variable. Then we can combine those 2. Okay, we cut out the one that is quote-unquote canceled out, and then we concatenate the rest. Does that seem or sound mechanical to you? We're just looking for expressions, disjunctive expressions in the CNF, where one disjunction has one variable, and then the other one has the negation of the very same variable. That's just search and locate it, right? And then the result is we can combine those two disjunctions, concatenate, and just get rid of the term that is quote unquote canceled out. Yep.
We have that on the board, right? Like we have B in one set, we have not B.
Exactly. So when you look at, very good. We can actually do two different resolutions here. We can resolve this one with this one, get rid of the B and the not B, then it becomes A or C or not D. We can also combine the other one, okay? We can combine this one with the last one, because one has a not D, the other one has a D. So when you get rid of the not D and D, then you have not B or C or not E. Yep.
So couldn't you just combine all of them together because there's
Yes.
Okay.
But you cannot do it in one single step. Okay,
Yeah.
that's the whole thing. Is each step can only locate two expressions where one has a variable, the other one has the negated of that same variable, and you can only cancel out one variable in one step. You cannot do two at a time. Yep.
Okay, after collapsing it together, we're
Yep.
gonna have one or then above it one and how do you rewrite it?
Okay, well, this is kind of doing a little bit ahead of time, but it does explain why we are learning about CNF. So I feel that it is still relevant to what we are talking about because it gives you a reason of why are we doing this. Okay, so let's do that resolution. So the first step is, okay, I'll do it on the projector. So this way it's easier to see for, it will be recorded for one thing. Okay. Okay, so I'll just rewrite the whole thing. This is A or B, and not B or C or not D, and E or not E. Okay, so I think I got this right.
Yeah.
Right? Okay. So the rule or the inference of resolution basically says if you see two of these expressions and they share, one has a variable and the other one has the negation of the very same variable, you can cancel those two and then keep the rest. Okay, so in the first resolution, I take out the B and the not B, then we can just concatenate the rest, and we end up with that. Is that okay? That's the result of resolving the first expression and the second expression on the first line. Okay. And then now I can say, oh, but one of these terms has a D and the other one has a not D. We can now cancel out those two and combine the rest. So now we have A or C or not E. And that's the answer. Okay. But in the end, what it really means is this infers this. That is the result. Are we still doing okay so far with just the individual steps of resolution? Yep.
I'm sorry, I missed what I was writing. What did you say infers that? The original equation
The entire original equation,
infers
the last
okay.
one.
All right.
Yep.
Thank you.
Yep. So in a proof, this is what we are doing. Because what we are doing in a proof is we are just inferring the next expression, inferring the next expression, inferring the next expression. Okay? So each one is basically one step of a proof. But at this point, what have we just proved? Okay, we have just proved one thing. Okay? The one thing that we have proved at this point is if this thing was true to begin with, this has to be true as well. But do we know whether this thing, the original expression was true or not? No, we do not. Yep.
So how do you want us to comment how what we're doing? You want to do this next to each line?
No. This is resolution. This is your next homework assignment, not the current one.
Yeah.
This is already in CNF. Your job is to convert something that is not in CNF into CNF so that we can do resolution. Because you cannot use the tool of resolution, which is what I'm demonstrating right now, until you have the entire WFF in CNF. That's why we are learning how to convert it. Okay. But then we still have the big question. How does this help us prove a theorem? That's what we are trying to find out, right? How do we prove a theorem? That depends on proof by contradiction. So what you do is you have a theorem, and then you have the rest of the stuff that you already know. So what you do is you introduce the negation of the theorem into the big CNF. And that whole thing should resolve to what? False. You should end up with just that one answer, which is false. Because if a theorem is true, and you combine that with all the other truths of the same world, then you should end up with a contradiction. Contradiction just means false. You basically go through all the resolution, and in the end, you end up with false. That is why, that's how you do mechanical theorem proving. So we are basically currently 2 steps away from being able to prove a theorem using the mechanical steps. But this is the first step. The first step is just, okay, if you look at this as cooking, we are just collecting the ingredients and chopping everything to size. Okay, but we haven't really started the pot yet. That's the cooking part. Is that okay? So we are slowly getting to the holy grail of being able to mechanically prove something, but this is the first step. This is the initial step. Are we doing okay so far in terms of taking one step back and just kind of look at this and go like, okay, but why are we doing this? It's because we want to prove theorems in a very, very mechanical way. Yep.
For the homework, we just have to make the 4 variables that we're given with into a conjunctive normal function.
Correct. So what in the homework assignment, you are given an expression that is not in CNF. So if I go back to the assignment, you are given this expression, which is definitely not in CNF. Okay, it looks like it's kind of CNF, but it's not. Okay, it comes close. Okay, because you can still see that overall speaking, we have some ands, but it is not in CNF because each component by itself is not in CNF. So this one is a little bit easier because you just have to deal with each individual component. Turn each one. Okay, if you turn this one into a CNF by itself, you turn this one into a CNF by itself, then you're done. Because the conjunction of any CNF with another CNF is a CNF. Yep.
So it feels like this homework assignment will be just about remove the implied sign and turn into other form.
Well,
because the other one's
not
already
quite that easy because the negation applies to Q or R, right? So you have to play with certain things, and it might end up with distributing stuff and whatnot. Yep.
So you don't want us to resolve this at all?
Oh no, there's nothing to resolve. Well, okay, I guess you can resolve it to a certain point, but there's nothing to prove yet. Okay. In other words, you can resolve all you want, but nothing will won't get to false. Okay. So there's no theorem here for you to prove, which is kind of the next step. Okay.
You said that there were 3 rules that we had to use for this assignment?
Yep, they're in the notes. Okay, so we'll go back and take a look at the notes here. Okay, there we go. So the why part, basically explains why normal forms are in generally useful. If you're in CISP 310, you already know why one form of CNF is, what one form of why particular normal form is useful. Because you guys are doing the subtractor in a DNF, not a CNF. Okay? Because we favor certain structures of gates in electrical engineering. But in this class, the other reason is just for mechanical theorem proving. And Prolog, which is a programming language just for that purpose, is dealing with CNF. Okay, it's just that we don't see it as a CNF, but everything really is expressed in CNF. All right, so here are the rules. But instead of talking about the rules here, let's go back to this example. Okay? And I know this is kind of like a gnarly example, even though it is very simple to begin with. Okay? The equal to is basically a double-sided arrow. It's equivalent to. So let's take a look at this one and see how we can derive it from one step to the next. Okay? All right. So we look at this. Okay, let me just kind of use my spreadsheet here. My text editor here. Okay, so we have P is equivalent to Q, and then this whole thing is equivalent to R. Okay. Is this in CNF? Obviously not, because I don't even see conjunction here. I don't see disjunction here. Okay. In other words, it's using operators that are not even allowed in the CNF. So the first thing we have to do is to change this so it does use things that we can use in CNF. So I will start with this and that. Okay. So the first one is something implies the second part, and the second part is just R in this case, and then this one is R implies the other part. The other part is nothing more than just P is equivalent to R. Okay. Do we have any questions about this? This one has no particular rule or particular name other than by definition, this is how we define equivalence. Okay, are there any questions about this? What is equivalence? If it only is. So when we have A is equivalent to B, what is the other way to express the same thing? A implies B, and B implies A. Does that look like it? It just looks messy because A is P is equivalent to P by itself. Okay. So now we have to do this one more time. Well, we have to take care of P is equivalent to Q. So that by itself is a little bit of a messy thing because, okay, I'll just do it separately here. P is equivalent to Q can be re-expressed as something and something else, okay? So we basically say this is P implies Q and Q implies P, okay? And I have this going into two places because I have it here and also here. So maybe I should do some simplifications first. What is P implies Q? That is not using conjunction either or disjunction. So how do we turn it? It becomes not P or Q. Okay, very good. So you guys remember all that stuff. Not P or Q. And I'm gonna just kind of switch over to the other way of expressing the same thing. Not P, not Q or P is the other one. Okay. Is this in CNF? Yeah, that's in CNF. So what I'll do is I'm just going to copy this. So okay, let me copy and paste, and then we just take out this chunk here because we already know what it looks like, which is this mess here. Put this here, put it here. Okay. All right, but we still have one imply to deal with, right? So we have to deal with that imply. But we already know how to deal with the imply. We negate the first one, and then we use a disjunction to connect to the second one, okay? So it's not really hard. It's just very, very mechanical. So we copy and paste this. Copy, paste, okay? And then we just say that, oh, it's really the same thing as negating this and doing an OR with the second part. Same thing over here. We negate the R, and then we OR with the second part. Okay. Any questions at this point? And I'm going to remove the word "and" so that everything is just using the electrical engineering notation. Are there any questions about this mess at this point? Yep.
This one's not in CNF because you negated both sides.
Oh, it's far from CNF because, okay, the first clue that this is not in CNF is we have a conjunction here. Yeah. And the second clue is we also have a disjunction and a negation that applies to the conjunction itself. So there's many things that's wrong with this one that makes it not in CNF. Okay? All right, but we're getting closer, okay? Because now we got rid of the equivalent to operation, we got rid of the implied operation. So now we only have negation, disjunction, and conjunction. Yep.
So at this stage, we only work on the first part, on the left hand side, on the left part of the end, right?
Say that again?
At this point, we only work on the left parenthesis side.
No, because there's a conjunction.
Well, there's a conjunction here.
Yeah.
This is one big mess, and this is another big mess.
Okay, at this point, we'll only work on the left big mess because the right one is here.
This one is not CNF either. It is not CNF because we have a conjunction here. And the conjunction has to be done before the disjunction because of the way I put the parentheses. So that will not meet the requirement of a CNF. But yes, but you are correct that we can work on one side at a time because once we convert the left-hand side to CNF, then we don't have to touch it anymore. Then we only have to convert the right-hand side to CNF, then we're done. Because the CNF conjunction with any other CNF is, the overall thing is still a CNF. Okay, so we can now work on one side at a time. Okay, we just focus on one side at a time. And let's just say that we focus on the left-hand side. Okay, so what is breaking the requirement, there are several things, but the one that I'm going to deal with first is I want to deal with this negation. Okay, that negation cannot be there because it is not applied to a single variable, and instead it is applied to what?
Conjunction.
It's applied to a conjunction. Okay, so we want to deal with that first. And which rule do you think is going to be helpful here? De Morgan's law. Okay, so we can use De Morgan's law. And over here, I basically use boldface to indicate what type of law you have to document in your homework assignment. So in De Morgan's law, there are two versions. One version of De Morgan's law is dealing with a negation on the outside and a disjunction on the inside. The other one deals with a negation on the outside and a conjunction in the inside, which is the one that we want to use right now because we do have a negation on the outside and a conjunction on the inside. So whenever you see something in this particular format, which is a well-formed formula, psi, well-formed formula rho, okay, like this, you can take the negation on the outside and distribute, quote unquote, distribute the negation to the inside, but then you have to change the operator from an and into an or. So we'll do exactly the same thing in our example. So we have a conjunction here. This is implicitly a conjunction. This is the negation on the outside that I want to, quote unquote, distribute into the inside. So the result of this is the conjunction becomes a disjunction, and then the negation gets distributed into the inside, and this is what we end up with. So on the side, in this case, I would have to use, say, De Morgan's law. The first few, I'm not gonna require you guys to write down, but you still have to do it step by step because in your homework assignment doesn't have its equivalent to, it only has implies. So one step, will turn it into this form. Okay. Are there any questions at this point? Yep.
So we're breaking, I'm just going to ask generally, we're just breaking down the very beginning statement that was given to make it into a good CNF, basically.
Yep. So you're basically just looking at the way I see this is I look at it from the outermost perspective and then say, okay, why is this not in CNF? And then I try to go from the outside in to convert it into CNF. All right, so we take a look. So let me just repeat what I just did. I took this part, okay, and used De Morgan's law and turn it into this part. Are there any questions about that step, what I just did? Okay. So I look at this part here and go like, hey, that is not good either, because I have a negation applied to a disjunction, and here I have the same thing. I have a negation applied to a disjunction. So I'm going to resolve that first. So I'm going to apply De Morgan's law again, but this is the other De Morgan's law, because this time I have a negation on the outside and a disjunction in the inside, not like the previous time. It is still called De Morgan's law. We have a negation on the outside and a disjunction on the inside, except you convert the disjunction into a conjunction when you distribute the negation into the inside. Okay, so we'll go ahead and deal with these two this time, and we'll just copy and paste. And because these two are so symmetric, if you want to do both at the same time, that's okay. Okay, I'm not going to take any points off. So once again, we have to distribute the negation and convert the disjunction into a conjunction. You can cancel out the double negation. There's no particular name you have to use. Just deal with it. Just get rid of those. And then the same thing over here. Okay. Double negation goes away. And if you want, the clarity, you can still use a parentheses around these things.
Wait, what is that? What is P not Q?
What?
What is P not Q?
It's P and not Q.
Oh, there's a.
Yeah, it's the result of applying De Morgan's law to this expression, and this becomes P and not Q.
Okay, so there's an implied conjunction there.
Right, it's kind of like, having the
Like
implicit
multiplication.
parentheses around not Q. Yeah, but since, negation can only apply to one thing, which is right after that, so normally we don't use parentheses. Yep. All right, so are we okay with this one? Okay, so let's take a look at this expression here. We have a disjunction here, we have a disjunction here. So that means I can remove all of the parentheses and it will still be okay. It's not in disjunctive, conjunctive normal form, but I don't need the extra parentheses. So let's go ahead and do that part. Control C, and then we Control V here. All right. So what I'm saying is I don't need the extra parentheses. Okay, if you want to keep some, that's okay. If you want to keep this one, that is okay. All right. So are we okay with this step? What I did was I took this expression and I say, hey, there are all of these extra parentheses that are not really needed. So I just turned everything into this form. Are there any questions? Nope. Okay. And now we focus on the right-hand side. Okay, so after all, oh, okay. I can't do anything about this. Okay, this is not in CNF, but I can't do anything about it. Oh, I can distribute. I can still use the distributive law on this one. Because distributive law in Boolean algebra is a little bit weird compared to the arithmetic one. Okay, because I can take something like this and convert it into something like this. Okay, are there any questions about this one? Okay, first of all, let me see if I can overlap these two. Okay, so just hold on a second. Let me scroll things a little bit so I can show the distributive law itself and the expression that we have here. So we have something like this, right? And the distributive law requires something to look like this. Do we have the right format to apply the distributive law?
No. Yes?
Yeah.
P not Q. Either side.
We have, okay, see in the picture here, we have the conjunction, which is the first operation, and then the disjunction is outside. And over here, we have the same thing, because we have P and not Q in the inside, and then the disjunction is on the outside. We only have to deal with two at a time, okay? We don't have to deal with all three terms at the same time. If you want to deal with all three terms at the same time, that's a little bit more complicated. Yeah?
So basically, P and not Q is a well-formed formula, making it phi itself, and then phi.
Correct.
Phi
Yeah.
and all that.
You can choose to break up one side or the other side. You can also do both at the same time. Okay, let's see if I can do both at the same time. Okay. Okay, so let's say you want to deal with both at the same time. So let's forget about or R at this moment. Okay, so let's say we want to deal with these two at the same time. So we're gonna do something like this, and then the rest would be the same. And this is using the distributive law. So what do we end up with in this case? We'll end up with P Q is 1, P or Q is 1, right? And P or not P, Q, wait. Okay, I said one thing, I typed in something else. P or not P, and Q or, oops, not Q. Not Q from the first expression, or Q from the second one. And then we have not Q or not P from the second one. Okay. So let me just highlight what I'm doing here. I'm taking this particular disjunction and apply the distributive law twice and end up with these 4 terms. Yep.
Isn't Q at this point it's allowed and still true?
Say again.
Won't it?
Oh yeah, but I'm not doing any simplifications just yet. Okay, all I'm doing is to mechanically apply the distributive law twice and end up with those terms. We'll do the simplifications later. I know there are things you can simplify. But is that making any sense? P goes here and here. Q goes here. Oh, excuse me. Not Q goes here and here. And then I take Q, apply here, P apply here, Q apply here, not P apply over here. It's just a cross product. Yeah. It's just every way that you can to combine all of those things. But the key is the conjunction in the inside now gets distributed to the outside, and then the or on the outside is now distributed into the inside. And which is what we have here. We have disjunction on the outside, that gets distributed into the inside, and then the conjunction, which is in the inside, is now on the outside. Are there any questions about these two, this particular step? Yep.
In the homework, would you want us to do that in 2 steps since you did 2 distributive steps in one?
For something like this, you can probably combine it into one single step, or you can say distributive law times 2. Because I'm actually combining 2 steps into one. Okay, so you can say x2. Okay. All right, but as somebody already observed, there are things that can be simplified. So let's see what can be simplified here. This thing here. What is P or not P?
Always true.
Always true, because one of them has to be true and the other one has to be false, because they're negations of each other. But in a disjunction, if at least one side is true, the whole thing is true. So we are guaranteed that this disjunction is true. Now this disjunction basically becomes true, but it becomes a part of a conjunction. What happens when you have a conjunction and one side is true? No, it's always the same as the other side, because
one side has
because true is the identity of conjunction. So that means there's no need to put a 1 here, so you just get rid of the 1. Same thing applies to this one, you just get rid of it. Are we still doing okay so far up to here? Now we have one last thing to deal with, which is the R. Okay. What do we do about that R? Yep, exactly. Just do it one more time. And does it fit this particular format? Do we have, conjunction in the inside and disjunction on the outside with our entire right-hand side here? Yep, we do. Because here's the disjunction on the outside, and then we have conjunction on the inside. So we end up with, let's see what is the result of doing this. So we have a another plus r here, right? And this whole thing plus, and another plus r over here, and then we don't have that anymore. Now, obviously, for those of you who want to have more consistency with the previous line, you can just look at all of these things as one particular thing. You're just distributing the r, the OR into it, and remember that we have to turn this into an AND. It is in CNF at this point. This whole thing is now in CNF because the parentheses are no longer needed when you have operators that are the same kind. Then you don't need parentheses anymore. So that means this pair of parentheses can go away. This pair of parentheses can go away as well. And I think I have some redundant parentheses on the outside, so I can get rid of this one and this one. So now we have a disjunction, another disjunction, and they are connected by a conjunction. So when you look at this sub-expression, which is just the left-hand side of the original thing, it is already in CNF. I'm done with one side. Now I want to turn the other side also into a CNF because the conjunction of two CNFs is a CNF. Okay? So now I look at the right-hand side and go like, okay, why is this not in CNF? Because we have a disjunction on the outside of a conjunction. Okay? And how do we resolve that problem? Yep, we applied the distributive law, but this is the other distributive law, and I did not mention it here, okay, which I should. Maybe I have that. Let me see if I have it. No, I forgot to mention it here. Okay. It's the opposite of this. If this is a conjunction and this is a disjunction, then it turns into, this one becomes a conjunction, this one becomes a conjunction, that one becomes a disjunction. Yeah. Yep. So when we apply that operation, then once again I'll apply two of them at the same time. So now we have not P, okay, I'm just gonna take out these two and replace it with something, or something, or something, or something. There are four terms. Each one is, this one, the first one is not P, not Q, not P, P. The third one is Q, not Q, and then we have QP here. Are there any questions about this particular distributive law? Yep.
We apply the same to R, not R plus that and plus not P plus Q. The line right before above it.
Second?
The line right above that.
Okay. Can we apply? Okay. Can we apply?
The same as what we apply on the left hand side.
No, it's not exactly the same because on the left-hand side, this is what we had originally. Okay, but over here, we have exactly the opposite because we have the disjunction on the inside and a conjunction on the outside. So it is still using the distributive law, but it's not. We just flip all the ors into ands and all the ands into ors.
Yeah, what I mean is I'm including the disjunction from not R.
Well, yeah, we can do that first. We could have done that first, but I do it in this case. I do the other one first. Yeah. All right. So out of these four terms, can we do any type of simplifications? When you see not P and P, you kind of have the idea that okay, we can probably do something about this. What can we do about it? Not P and P is guaranteed to be false. Because in a conjunction, if at least one side is false, the whole thing is false. But between P and not P, one has to be false because they're negations of each other. So this conjunction is guaranteed to be false. So we just say, okay, this is false. And the same applies to Q and not Q. It has to be false. But when you have a disjunction operation, anything or false is just anything. Because false is the identity of disjunction. So now we get rid of this guy, we get rid of this guy. Okay. Is the right hand side in disjunctive normal form? Conjunctive normal form. Is it in conjunctive normal form, which means the conjunction is the last thing that you do? No, it's quite the opposite. This is in D and F, not in C and F. So what do we do about this? Well, which part is the offending part?
Or outside the front.
The or applied to conjunction, right? That's the offending part. We can have a disjunction. This whole thing can be disjunction of something, but it has to be disjunction of individual elements. But right now it's not. Okay, so we can look at this thing here and say, can we do something about this? We have seen something like this already. Well, similar, but not exactly the same. Yep. So we distribute the or, which is exactly what the notes already has, and also kind of what we did earlier, except it's not. Okay, look at this one here, and look at this one here. Do you see the similarity? Okay, so we have to do the distributive law again. So we say distributive times 2. And what do we end up with? Let's see. All right, so we are taking care of this particular thing. It ends up with 4 components, but they're all connected by conjunction. Each one is a disjunction because we are turning all the disjunction in the inside into, we're turning all the conjunction in the inside into disjunctions. So the first one is combining the first component of the first conjunction with the first component of the second conjunction. First component of the first one, second component of the second one. And then we have the second component of the first component of the second one, and second component of the first, second component of the second. Is that okay? Yep.
Can you eliminate the ones that
yes, we can,
not P and
but
P?
I'll do it in the next step. So in the next step, I look at not P or P. That is just 1, but since this one is in a conjunction, it is not useful. Once again, we turn this one into a 1, but since it's inside a conjunction, it is not useful. So we end up with something like that. Do we have a conjunctive normal form at this point? Close, but not yet, right? Why don't we have a CNF now? That not R on the outside is messing up things, right? How do we take care of that? We distribute. Yep. So once again, we apply this derivative again, and the end result. We now have 2 components left, right? They will be connected by a disjunction, but each one is going to be, this is going to be not R or not P or Q. This one is going to be not R also, or not Q or P. That. In the next step, we can just eliminate the unnecessary parentheses. So we take this one, put it here, and I know this pair of parentheses is not needed because both levels of these operations involve the same type of operation. So I can get rid of this pair of parentheses, I can get rid of this pair of parentheses. And now what do we have on the right-hand side? And when we just kind of focus on the right-hand side, do we have a CNF?
Yes.
we have a conjunction of disjunctions, and inside the disjunction, we only have either variables or negations of variables. Okay? All right, but let's take a look here. Okay, we still have some extra parentheses that we need to take care of. Because the right-hand side is a CNF, the left-hand side is a CNF. There's a conjunction here, there's a conjunction here, there's a conjunction here. In other words, we have two levels of conjunctions that are connected to each other, which means we can flatten it. Okay? So the way we flatten this is simply to get rid of all the unnecessary parentheses. And now we have, oops, one more.
So right now you're doing the resolution?
Nope, there's no resolution. This is the final answer. This is, we're all done. Yep. I forgot my row sheet again.
Basically just the green choice there, just flatten everything, right?
The flattening can only be done when you have two levels of operators and they're exactly the same time.
So that's how you ended up with the ABC green right there, right?
Correct, but they erase the other one.
Yeah.
Yes, because the other one has just C, A, B, like that.
Right.
But because this is a conjunction, this is also a conjunction, that makes it possible for me to collapse. But that's what I just did actually. So are we doing okay so far with this? Yeah, go ahead.
You said there were three
Right, there are two De Morgan's law and then there are two distributed. So I should have said that there are four, quote unquote, four rules, but two belong to the same category. We just say distributed, and then two belong to De Morgan. So we just say, okay, De Morgan or distributed.
Fix it in there?
More or less. I don't think it works perfectly. I was gonna do another go about, but there's not enough time to do two.
Well, what are you gonna do in like test cases? Yeah. There's what, 60 test cases?
I mean, redoing two from the middle. Even if I could do that within 10 minutes, but connecting all the wires, taking apart all the wires, making sure it didn't ruin anything, that'll